Okay. So we continue the lesson for logarithms. So if you remember, I was just trying to give you main properties of logarithms. So if I remember correctly, we had these two, or maybe three. So we had this, that if A is positive and if A is not equal to 1, then we have the log of 1 in base A to be 0. So we can say that if A is an acceptable base, log of 1 in any base is 0. And then we also learned that log of a number in its own base, regarding these conditions are met, this is 1. And then we also learned that the definition of logarithm can be written in a nice way, saying that if I have A positive, A not equal to 1, and if B is positive, and then if I have A to the power of log of B in the same base A, then the answer simply becomes B. So we talked about these. So this is essentially the definition of the logarithm, but a very useful one. And then we also learned that if x is positive, if y is positive, well, let me write it exactly the way that I wrote, I think. So if a is positive and not equal to 1, and if x is positive, y is positive, under all these conditions, you can say that the logarithm of the product x times y in the base A, the interesting property is that it becomes log of x in base A, log of y in base B, in base A, but this is a product. You are not allowed to put product. On the other hand, you have to put addition here. So we prove this rule. That's extremely important rule. So if you have a log of a product, you can write it as the sum of the logs. And if you have the sum of two logs with the same base, if you want, you can collect it and write it as the one single log. But the condition is that you have to respect to change addition to multiplication. And we also prove this, not just memorize that. We really understand this is essentially nothing except this rule that a times m times a to power n is a to the power of m plus n. So that was essential to prove this. Of course, it doesn't matter if you have more than 2. Yes. So, for example, if you have log of x times y times z in the same base, in base A, if x, y, and z are all positive, then if you want to, you can write it as log of x in base A plus log of y in base A plus log of z in base A. So in principle, this can be extended to more than 2 variables. For example, if I ask you, can I don't know, for example, like this. Now let me just take these brackets. If you want to, I'm not saying why we should do that. Assume that you want to, you can write it as log. Instead of 35, you can write 5 times 7 in base 3. And then if you want, you can write it as log of 5 in base 3 plus log of 7 in base 3. Yes. So I want you to understand that this equality is actually true equality based on this property. But sometimes, of course, this is useful because you can simplify. For example, assume that I have given you this, but instead of base 3, I gave you base 5. So for example, if I gave you log of 35 in base 5, so what you can write log of 5 times 7 in base 5, and then what you can do, you can write log of 5 in base 5 plus log of 7 in base 5, but there is a better name for that. Log of 5 in 5, according to the first property, is just simply 1. Yes? So it is important to understand sometimes expanding makes the problem simpler. Or for example, if I say log of 12 in base 2. If you ask me about the numbers, I cannot answer you. I have to use the calculator. This is asking you what is the number so that when 2 is raised to that power, it becomes 12. I cannot calculate it on top of my head, but I can simplify it a little bit. For example, I can, instead of 12, I can write 2 times 2 times 3, or it might be better, yes? For example, I can write it as 4 times 3 in base 2, and then I can write log of 4 in base 2 plus log of 3 in base 2, yes? And then this one I can do it in my head, yes? Log of 4 in base 2 is what? 2. 2. This becomes 2, but this one I have to live with it. I have to write it. If I want to write exact values, I have to keep it as that. Otherwise, I have to put this in the calculator, and I will tell you how to put this in the calculator probably today or tomorrow, yes? So that is an important property. So if you ask me what is log of 2, I don't know the exact answer. By the way, when I don't write this base, it means it is 10. So when I ask you log of 10, a log of 2, it means that can you give me a number so that when 10 is raised to that number, it becomes 2? I don't know. I have to calculate using the calculator. And if you ask me the same question for log of 5, I will tell you the same thing. But if you ask me for this, I can immediately answer you. What is the answer? Yes?
1.
It's 1. This number is definitely exactly equal to 1, yes? Because I want you to learn in both directions. Sometimes this is given and you need this. Sometimes this is given and you need that. Yes? So here, what is not written here is just this 10. Yes? So you have to imagine that 10 is there. And then I can use this direction to go back. Yeah? So what can I do? I can write log of base 10, which I don't need to write. But then this is the sum I have to multiply. Yes? But 2 times 5 is just 10. And now I am asking what is log of 10? The base is also 10. So the answer is exactly 1. So these kinds of things that you need to be able to calculate. Any questions? Okay, so let us continue for another interesting property. So this was number 3. So let me write number 4 now. So I want to talk about something like this. A log, and I have some x here to power p, and then I have base here. So because this appears as a base, I would say that a should be positive and not equal to 1. Then I am claiming that this number can be taken down to the back of the log and be multiplied by the log. So this becomes p times log of x in base a. So then it means that x should be positive, and p is any real number that you like actually. Of course, if x is positive, you don't have any problems with p. So that's extremely important property. If you have a power on top of the number sitting in front of the log, if you want, you can move p to the back of the log and multiply it by the log itself. So, for example, if I ask you what can you write for something like this, x to the power of 3 in base A, you can write I calculate log of x in base A, I get a number. Whatever that number is, I multiply it by 3. So this means that this power actually goes back here. We want to prove this. Why this is the case, that the log can just survive. So everything that we want to prove about logarithms reduces itself to a problem among exponents and powers. And that's just, we want to translate it. Okay, but let us just do it together. Do you remember how I did it for one of these cases? Yes? So we want to prove number 4. So I would say that let me give it a name. I will call log of x in base A to be m. Okay, so then you should be able to help me to continue the rest. So I want to convince myself this is the case. This is the standard way of proving things about logarithms. So you give them a name and try to use the definition of the logarithm. So if you let me to give this a name m, then based on definition of log, you have to admit that a to power m then becomes x. Yes? Okay, but now what is the next step? You need to get some motivation from what you are supposed to prove. If I give this a name m, then look, this should also be m. So you give it, so this is m in your head, but it is multiplied by p. So this means that p times m is needed. Okay, I have this one, I have m on top, but I do not have pm. But I want to make something that pm appears. So what should I do there? Because if you just look at the problem, it doesn't become clear. So you see what is your goal? Your goal is to prove this equality. I don't know what this is, but I know this is p times m. So can you tell me to do what so that at least pm appears somewhere?
Wait, like, because we don't have p anywhere in our equation, so would we say that x is equal to, like, well, not x to the power of p, but...
Yeah, that's correct.
Or
We want to make x to power p. That's also a good indication, by the way. What you're saying is correct. The x to the power of p is also somewhere in what I want to prove. But x here is alone. I want to have x to power p. I have x, but I need x to power p. So this motivates to do what?
right out p.
To raise to power p. Yes?
Is the entire log raised to power p, or is it...
No.
What
Just x.
Okay.
would you...
So if I want to write like that, then it means I have to respect and put this on. Okay? And by the way, this is the way that I don't like. Usually in books they don't write like this. This is convention. They put p on top of log. Yes, that's also a good question, by the way. I want you to write it somewhere. If I mean p is for the whole logarithm, either I have to use pair of brackets around that, or by convention I put p on top of log. Then that's what you. But here I mean x to power p, a number, and I take a log. Yes, if you want, you can put a pair of brackets around that, but this is by convention not needed. Okay, anyway, I want to have p x to power p. So it motivates me to construct it. So if I want to have x to power p, I have to raise it to power p. But if I raise the right hand side to power p to keep the equality intact, I have to raise the left hand side to power p as well. Yes? But then this immediately appears, yes? I have another rule of powers. A to power m raised to another power, so this becomes a to power p times m is equal to x to power p. Yes? So we can keep it like this. We can use the definition of logarithm, but might be that's a little bit confusing for you. So let us keep it like this. But then let, for example, logarithm of x to power p in base a be called n. Let me call this n. Then immediately you have to admit that a to power n is equal to xp. Let me call this one number 2. What can I conclude, by the way, from number 1 and number 2? So if I call this one, sorry, I forgot to call this number 1. So number 1 and number 2, what can I conclude? Can you tell me? This tells you that a to power n is equal to x to the power of p. This tells me that a to power pm is equal to x to power p. So what can I conclude? Yes?
That a to the power of n is equal to a to the power of pm?
Yes, exactly. So let me write it the way that you mentioned. A to power n is equal to what? A to power pm. Yes? But now look, in the beginning I told you that a is a positive number and not equal to 1. Now you realize why this is extremely important that a is not equal to 1. Because I want to conclude, what do you conclude, by the way, from here? If a to power n becomes equal to a to power pm, what can you conclude? Yes?
N is equal to PM.
N is equal to pm, but under this condition, this is extremely important here. Because if a is equal to 1, then there is no guarantee. Because, for example, 1 to power 5 is equal to 1 to power 10. Yes? 1 to power 5 is equal to 1 to power 10. But can I conclude 5 is equal to 10? That's nonsense. So that is extremely important. You see, this assumption is needed. So a is not equal to 1 by my assumption. Now you are right. If a is not equal to 1, and of course a is positive, they are defined, then it means that there is only one option left, and that is the power. The power should match. Sorry, the exponents should match. Yes or no? Yes. Okay, but we are done. Why? Because what was the name? What was n? N was this guy. P times m. What was m? M was this guy. Yes? So we were able to show that this is indeed the case. Yeah. Is that clear? So this is a standard trick. When you want to prove some theorems in logarithms, you give them names and try to use the definition of the logarithms, write them in an exponential form. And use one of the properties of exponents and powers to be able to extract some information regarding the corresponding logarithms. Is that clear? So remember, I really want you to memorize these things because they are not that hard. For example, let me write something here for you. So if I ask you, how can you calculate? Not calculate, I want to write something that I want you to understand. So if I write something like this, if you want to, you can take 3 to the other side. By the way, these equalities are exact equalities. So whatever this number is, it is exactly 3 times larger than this number. So this is 7 to power 3. It is 343 or something. And then you move it to the other side, yes? Yeah. So this means that the logarithm 7 to power 3 is 343 in base 5. So this number is exactly 3 times larger than this number. But if you ask me what this number is, I don't know exactly. If you ask me what this number is, I don't know exactly. Yes? But I know whatever they are, this one is exactly 3 times larger than the other one. Okay, so now, for example, logarithm of 6 to power minus 4 base 2. If you want to, you can move minus 4 to the back of the logarithm and by the way, this operation is multiplication, yes. For example, if you want, you can continue a little bit more. Instead of logarithm of 6, you can write logarithm of 2 times 3 in base 2, and then you can expand that. So it becomes minus log of 2 in base 2 plus log of 3 in base 2 based on the previous theorem. But this is just nothing except 1. I can multiply 4 in. It becomes minus 4 log of 3 base 2. So without exactly knowing what these numbers are, we are establishing relations among them. And that is important. So you need to know this number, whatever it is exactly equal to this number, whatever it is. So it doesn't matter if these are fractions, by the way. So if I have 7, for example, to the power of 3 over 2, and by the way, 7, if I put 7 here, how can I calculate this? I can calculate this one in 2 ways, yes? I can ask myself, what is the number here so that 7 raised to that number becomes 7 raised to 3/2. So what's that number? It's 3 over 2, yes? Because I am asking you, give me a number so that when I raise 7 to that number, it becomes 7 to this number, sorry. Yes, so what's question mark? It's 3 over 2. But if you want, you can solve it using this trick. Because you say that this power appears here, I put it back, so this becomes 3 over 2, and what is left for me is log of 7, the base is also 7. But log of 7 in base 7 is 1, so this becomes 3 over 2 times 1, which is 3 over 2. Yes?
Is this useful in reverse?
Yes, sometimes it is also useful in reverse, yes. Sometimes you have something here, you put it back on top. For example, how do you calculate? Do you remember? 2, 3 log of 7 in, so let me make 7 smaller. 3 base 2. Of course, we were able to solve it in a different way, but now we can solve it also using this formula. So do you remember how we did it before? This you should be able to answer. Yes, I told you that if you want to calculate this, you can write it as 2 to the power of log of 3 in base 2 and then raise it to power 3, yes? But this and this are the same, so this becomes just 3 and then you have a power 3 there, so it becomes 27. But now you learn this new rule. So you say that this number is in the back of the log, so I take it and put it on top here. So then what happens? So this becomes 2, and then you have log of 3 to power 3, but the base is 2. Now this base and that base are the same, so everything cancels out, and then 3 to the power of 3 is left. The 3 to the power of 3 is 27. So that is 2 ways of calculating the same thing. So whenever you learn some equality, it is extremely useful to learn it in 2 directions. Sometimes, maybe most of the time, you need to move P to the back, but sometimes you need to be able to move P on top. Yes? Okay, so let me ask you one question. For example, what do I have something like this? If I have something like this, log. So do you agree that this is correct or not? So log of 1 over 2 base 3 is minus log of 2 base 3. That's extremely important and useful. So why this is correct? Yes?
Wait, is it because like something raised to the power minus 1 is going to be 1 over that?
Yeah, exactly. So this means that the left hand side here, instead of 1 over 2, I have another name for 1 over 2. It's not very common, but that is true. Instead of 1 over 2, I can write 2 to the power of minus 1. And then, as Melchior mentioned, this minus 2 goes back. So this becomes minus 1 times log of 2 in base 3. But minus 1 times any number is negative of that number. So you see, it's extremely useful. I interchange that, I put a minus sign here. Yes? For example, a log of 1 over 27 in base 3. Of course, you can immediately calculate the answer using the definition, but if you want to, you can use these properties, mixture of these properties. So for example, here I can write log, instead of 1 over 27, I can write 1 over 3 to the power of 3, but I can bring it up and make it negative. Then I can take this and put it in the back of the log. It becomes minus 3 log of 3 in base 3, but log of 3 in base 3 is 1, so it becomes minus 3 times 1, and it is minus 3. Of course, it was also easy to guess in this case the number. I am asking for which number 3 to that number becomes 1 over 27. Might be you should be able to also guess it. But that's also important to be able to do these calculations fast. Okay, now let me ask you one question. We learned that log changes multiplication to addition. Yes? But now can you tell me log changes division to what and why? So I want to add it here now. So that was number 5. So if you don't mind, let me clean this here and write number. No, that was number 4. Number 5 now. Number 5. So I would say that let a be positive, a not be equal to 1, x positive, y also positive. I am asking what happens if I have a log of a fraction. I learned that the product transforms to addition. But now I am asking you the same question for division. What do you think will happen in this case?
Subtraction.
Yes?
Log of x to the base a minus log of y.
Yes. So it becomes minus. So it becomes subtraction. The log x a minus log y a. But can you tell me why? Why? Yes?
Because of the rule that x to the power of m over n is equal to x to the power of n minus x to the power of n.
That is, yes, that is possible. You will start from scratch, giving them names and start from scratch. So what here is mentioning actually is that we give this a name m, we give this a name n, and try to do as before. That is definitely possible. But if I don't want to start from scratch, do I have an alternative now? It's always useful in mathematics to not start from scratch when it's possible. Yes? What can I do? I can prove this using two properties. One property is this property, and one property is the product rule. So log of x over y in base A can be viewed as a product. Yes, I can see it as x times y to the power of -1. Yes, is that right? Because x over y means x times 1 over y. But 1 over y is nothing except y to the power of -1. So that is correct. But now what you see, this is a product. You already know the rule for the product. The rule for the product is to write the log of the first one plus the log of the second one. But we also learned that -1 is a power, so it goes back. So what happens? It becomes log of x in base A plus -1 goes back. But nobody writes plus -1 because plus -1 is just minus sign, yes. We are done. So that is also good to remember. I hope that you memorize everything so far because they are very easy. Okay, so I want to ask your opinion about this one. If I ask you to, this is very important, very important. I mean by very important because I want you to do it fast. Understand it once for all and do it fast, okay? So for example, if I ask you, I have the log here, so let me use Greek letters not to get confused. So here, I would write, I put A here, and then for example, I write x to power alpha, multiplied for example, y to power beta, and then for example, I divide it by z to power gamma. Okay, I have this combination. I want to expand this expression as much as possible. Okay, I want to do it once very patiently so that you learn, and then I want you to be able to do it immediately without doing the intermediate steps because that is too boring if you want to do it every time. So I want you to expand this expression as much as possible. Okay, I do it step by step. First, if I want to do it, what I see a fraction. If I ask you read this expression, you don't read it. You say that this is the division of this and that. So it's a fraction. So I have to use the fraction rule. So the fraction rule tells me that the log of a fraction can be written as the log of the numerator minus the log of the denominator. Yes? So this becomes the log of x to power alpha times y to power beta, of course in base A, and then minus log z to power gamma to base A. Is that understandable? So I use the first rule. But now the product rule can help me. And I can write it as what? Log of the first one, alpha A, plus log of the second one, y beta, y to the beta A, and then minus log of z to gamma A. And one more step, I can bring all these exponents to the back of the log. So what happens? This becomes alpha log of x in base A plus beta log of y in base A minus gamma log of z in base A. Yes? So that is expansion. But I want you to do it And when I tell you this, I want you to understand immediately that you can expand it up to this point without doing it step by step. But I want you to understand 3 theorems are involved. This is important. Which theorems? Fraction theorem, product rule, and this exponent rule. Yes, 3 theorems are involved. And then let me just exactly immediately mention, we do not have any formulas for the sum and the difference. So don't get confused. I don't know. There is no specific formula for this. If I give you log of x plus y to the base a, you have to keep it like that. Okay, so it's not possible to calculate. Of course, if I ask you what is this log, can you answer me? That's 1, because this bracket means giving the priority to this addition operation. But 1 plus 9 is 10, this becomes 10. I want to calculate log of 10, which is 1. But if I ask you what is log of 2 plus 7, then at most you can write log of 9, nothing else. You cannot write log of 2 plus log of 7 or whatever. Okay, let me ask you another question. Can you expand this as much as possible? Okay, if I ask you to expand this in base 2, how do you answer immediately? To expand this expression as much as possible. Yes?
Are you supposed to put a multiplication thing in between the...
So just read it for me. I want you, don't go through the steps. I want you to give me the final answer.
No, but are you supposed to put a multiplication thing in?
Yeah, if you want, you can put, yes. So what's the answer then?
2 log base 2 x.
2 log x to base 2.
Yes. Plus
3 log y to base
2
plus
c
4 log.
4.
Wait. No, it's c log.
So we are here.
Oh yeah, sorry. It's 4 log c
Base
base
2
minus 3 u
log
u
base 2 and then
minus
again minus
2 log
t base 2. Yes? That's extremely simple. And the other way around. Can you collect this back?
Yes.
I don't know. For example, minus 2 log of x plus 5 log of y minus 2 log of z. If I want you to collect it back as much as possible, immediately, what's the answer?
It's log of
You put a log with the same base if the bases are the same. If the bases are not the same, then you have to put the bases the same in one group.
and then y to y.
So the positive one is this one.
Yeah.
So it becomes y to the power of 5 divided by x to power 2 z to power 2. And then you can write it. So you should be able to go back and forth between these cases. Of course, if I write something like this, do you think it is wrong or correct? If you tell me this, and I write it like this. Do you think it's wrong? No, that's also correct. But usually my preference is to avoid negative exponents if possible. So you can only use the product, but then you have to remember, you are not allowed to go to the denominator. But if you go to the denominator, then you have to take the negative side. Yes? So you need to choose which one you prefer for that problem, but not both. Okay. These are the only formulas expressed in the book, but I want to add some more to it. Okay? So these are, I don't know why they are missing, but they are extremely important actually. So, one problem is this. So it means that in the exam, I will not ask questions that needed these ones directly, yes? So the first question is that I want to ask you, for example, if I give you log of 3 and then I put 2 here, in front, if I write 5 there, you know what to do. So what we do, we just write what? 5 log 3 2. Now my question is that I give you the same thing. I give you the same thing, but this time I put 5 here. Okay? I don't know, might be there are no nice relations here, but there is a nice relation. I want to take this again to the back of the log. But can you discover what is the correct way of doing it? If the power appears here, we'll just take it to the back. But if for some reason the power appears here, what we can do? Can we still put it in the back? Or we have to do some changes and then put it to the back? So that's another formula that we want to discuss.
Is it log 3 base 2 divided by 5?
Yes. How did you come to that conclusion?
Because if the base is to the power of 5, then if when you have, for example, the 3 to the power of 5, if you move it to the back, then it's multiplication.
Yeah.
Then if the base is to the power of 5, to move that to the back, it has to be 1 over 5, or just divide.
Okay, so that is your motivation. But actually you came up with the correct answer. So what he is telling is that if you want to move it to the back, you find the reciprocal and put it to the back. So if this is 5, its reciprocal is what? 1/5. And then you write the same, log of 3 in base 2. So that's very interesting. So if you have this power, which is in your book, you just move it to the back. But if you have an exponent here, you don't just move it to the back. You calculate its reciprocal. What by reciprocal I mean, it is 5 over 1. Reciprocal means that I interchange these two. Then I put it to the back and calculate the log. Okay, so in principle, I want to add this and then prove it, yes? So we want to say that if I have log a to some power p, and then I have b here, this becomes 1 over p log of b in base a. Yes? So in principle, a should be positive, a shouldn't be equal to 1, p shouldn't be 0 in this case. And b should also be positive. Yes?
Why is that?
Yeah, we want to prove it. Why this is the case. So I think you learned by now what to do, yes? So we give them names. So for example, I would say let me change my color. So I would say let me call this one log of b in base a. Let me call it m. And let the other logarithm be n. So you see, I am using the same trick over and over again. So I start from here. When you say that the log of b in base a is equal to m, what can I conclude immediately? That a to power m is equal to b. Yes? And when you tell me that the log of base of b to the base ap is n, okay, can you tell me what can I write in front of it?
AP to
AP to the power of n is equal to what? But there is another name for this based on the power rules. What is that? P times n is equal to p. So let me call this one number 1. Let me call this one number 2. What can I conclude from 1 and 2? What can I conclude? This one is b, this one is also b. So this means that a to the m is equal to a to the pn. But again, because a is not equal to 1, I can safely conclude that m is pn. And because p is not 0, I am allowed to divide by p. So this means that 1 over p times m is n. Yes? But put them back. 1 over p is just 1 over p. What was m? M was this guy, yes? Is equal to n. But what was n? N was this guy. Yes? So we learn now that if p is there, just move it to the back. If p is there, find the reciprocal and move it to the back. Yes.
What if the base and
Then you can combine them.
then
I will give you examples. Yes. Yeah, but let me just write it immediately here for you. So what he asks is that if I have log of a to power 3, let me write. If I have b to power 3, but a to power 2, how can I get rid of these powers? This 3 goes back, but this 2 becomes 1 over 2 and goes back. And then what is left is log BA, but nobody writes 3 times over 2. People write 3 over 2 log of BA. Yes? For example, let me see. So what happens, for example, if I have this? Do you agree that this is correct and why?
Yes.
So why this is correct? Yeah, you need to learn these gymnastics with logarithms, yes. So you see, what can I do? Here, the left-hand side is equal to, instead of square root of a, people write a to the 1/2. And then I have b here. But can I move this exponent to the back? Yes, we just learned, but the price that we have to pay is to find the reciprocal. But the reciprocal of 1 over 2 is 2. So this becomes 2 and goes back. But now 2 is there, so you can put it on top here. So then it becomes log of b squared in base a. So it means that I took 1 over 2 from here, moved it to the back, and then move it up. Is that clear? Yes or no?
Yes.
Okay. So that is one question I wanted to answer here. There is also another question. I told you that if you want to calculate this using your calculator, if you have a little bit old calculator, so usually the standard buttons on the calculator are LOG and LN. This LN we will study in Math 3C, But for the time being, this is the only one. So it means that you can calculate logarithms in base 10 using the old calculator. But it doesn't mean that using the old calculators you cannot calculate this number. But you need to learn something. There is a very nice relation, even though when I was seeing it first, I was a little bit shocked. Yes? The answer is very nice. The answer is that you calculate by log of 2 using your calculator button, and you calculate log of 3, and very strangely, you divide them. It becomes log of 2 to the base 3. It's extremely a surprising result. It was really surprising for me when I was at your age. I don't know, because they are not related in that way. But anyway, this is true. Log of 2 in base 3 can be calculated of log of 2 in base 10 divided by log of 3 in base 10. Yes, we want to understand this. By the way, this is not base 10. The reason that I brought base 10, because base 10 is your calculator. I can move to any base that I like to. For example, I can take log 2 base 3. I don't like 3. I don't like 10. I go to 7. So it becomes log of 2 in base 7 divided by log of 3 in base 7. That's also correct. So that is called the base change formula. I don't know, this is a very important result. I don't exactly know, because in the previous books it was absent. But I want you to know about this. So if you have a logarithm, whatever the base is, if you don't like that base, you can move to any other base that you like, but of course this number should have the property of being a base, meaning being positive and not equal to 1. But of course, the best one is 10. Or later we will see that's a natural logarithm with ln. But for the time being, why this is true? Okay, so let me just write the formula, the base change formula here for you. And try to see why this is true. So, for example, assume that I have log of b in base a. If I want to, I can switch to another base. But I have to write the log of this number in the base that I like, provided that I have to divide the log of the base in the new base. So the conditions are this. A should be positive, A should not be equal to 1, B should be positive. But C should be positive, C should be positive, and C should not be equal to 1. Because this is supposed to appear as the base of a logarithm. So under these conditions, this is a very, very important formula in the lesson of logarithms. So why this is true? Why this is true? Again, the same story. If you want to prove a theorem in logarithms, the same trick. Yes, do you want to say something, Rasmus?
Yeah, we could, in an attempt to get rid of the base a, we could instead write c to the power of something, so that we could move that power out. And it just happens to be that c, that was one of the formulas, that c to the power of log base c of a is exactly equal to a.
Yeah, exactly.
And then we can move.
So if you don't mind, but from pedagogical point of view, I will follow my strategy, but that's exactly the same thing. So what we say is that let log of b in base a, let me call it m, let log of b in base c, I call it n, and log of a in base c, let me call it p. Okay, so let me make it simpler. So what can I conclude from here? A to power m is b. What can I conclude from here? C to power n is b. What can I conclude from here? C to power p is a. Yes, that's understandable. But as Rasmus mentioned, I want to get rid of, for example, between these two, n and p, which are these sides, I want somehow to get rid of c. Okay, but how can I do that then?
Raise c to power m.
Or might be, it's easier to put these two here. It's more natural, yes. Instead of a, I put c to power p. So it becomes c to power p to power m. Yes? On the right hand side, instead of b, I put c to power n. Yes? And I am done. Why? Because this means c to power pm is equal to c to power n. And then c is not equal to 1. So I can conclude that pm is equal to n. So this means m is equal to n over p. But what is m? M is this guy. What is n? N is this guy. And what is p? P is this guy. So it's actually nothing except the rules of powers written in a little bit disguised form. Is that clear? Okay. But now I have a surprising answer at something. I also really enjoyed this. Log of 2 base 3 can be written as 1 over log of 3 base 2. It's also very astonishing. Yes? It's very nice gymnastics that you need to learn with these logarithms. So why do you think this is true? So if I have log of 2 in base 3, if I want to swap them, there is a way to do it. You just write 1 over log and then just simply swap them. Why is that? Yes?
You make the top one with the same base as
The number, exactly. So here, I told you that if I am interested, I can switch to any admissible, plausible base. I switch to base 2. Yes? So log of 2 base 3, I switch to base 2. It becomes log of 2 base 2, log of 3 base 2. Yes? Is that understandable? This is the base change formula. But now log of 2 base 2 is just 1. So that's the best way to understand this. Yes? So that's also extremely important. Let me just put it here somewhere. So, if A is positive, if A is not equal to 1, if B is positive, and B is not equal to 1, this is the more or less last formula I want to bring it up for you. So log of A in base A is equal to 1 over log of B in base A. Extremely handy formula when you are dealing harder problems in logarithms. Yes? But let me make sure everyone understands that why this is a consequence of the base change formula. So if I ask you log of A in base A, I just told you that if you want to, you can switch to any base that you like. So I switch to base A. Then it means AA, BA. Yes? and then this becomes 1, and I get that formula. Yes?
Can we continue infinitely?
What do you mean by? For example,
Well, if we change this log of b and in base a back to log of ab.
but then you go back to the same. So I mean, you cannot continue. You will go back.
Oh, you
Yes.
can.
But you can go to other bases.
Well, no, but like you could do that. It wouldn't have any point in doing that. But
No, sometimes. I mean that if that is just interesting, that's the point. Because every time you do mathematics, we are looking for something interesting. And if you think that's interesting, yet just please tell me. Because what I see is that you say that let us repeat this once more. If you repeat this once more, you'll go back to this one. Yes? But let me ask you one question. What is this one? So log of 2 base 3 multiplied by log, let me write dot. Log of 3 and then times log of 10 base 7. Can I write this as log 2 base 7? So might be this is what you mean by going infinitely many years. So can I write something like this? I am multiplying. Do you know that I do not have any formulas for these products? Because the product is between logs. Is that right or not? I don't know. So I told you that if in the change base change formula, it's very good if you go to base 10. This is probably the best and simplest way. But of course, you can go to any other base that you like. So I want you to write this separately somewhere. Okay. So then, for example, the left-hand side of that expression, log of 2 base 3 can be written as log of 2 divided by log of 3. Log of 3, I keep it as it is. And log of 10 in base 7, I can write it as log of 10 in log of 7. Is that understandable? So what I have written, instead of this, I have written this. The middle term, I have kept it as it is. The last term, I have written it in that way. But then, whatever this log 3 is, that is the same log 3. One of them is in the numerator, the other one is in the denominator. So they are cancelled. Yes? And then log of 10 is what? 1. So this becomes log of 2. By the way, when I cancel, that's also 1 left. Log of 2 times 1 times 1 is just log of 2. And then 1 times log of 7 is log of 7. But log of 2 divided by log of 7, if you insist, you can combine this as this one. Yes?
oh yeah. So does that mean that like we can always like combine a products of logs in any basis?
Yes, yeah, and then if you see that there are something in common, we can cancel them out.
That's great.
Yeah, it's very interesting. I was very excited when I was at your age, but there are more interesting things to be excited about these days. Okay, so That's a very nice thing. So I want you to learn. Whenever, I don't know why this is missing. Might be this is still in the book. I haven't checked the book. But these two formulas, the one that I told you, usually they don't appear in the normal texts. So if you have a power here, what happens? If you have a power here, we learn 1 over p log of b base a. And then the base of this is the most useful way of writing it, but of course you can go to any other base, not just 10. But that is extremely useful. And that is also a very, very nice way of doing things. So you can view this one in this way as well, by the way. Log of a base b. I can go to log, no, you have to, yes, that is correct. You have to go, so that's good. The way that Sergey mentioned is actually good. And then I will write a challenge problem for you, but that is if you are interested. So if you have a, that's also very interesting. And then you have the power of log, but that is not repeated. For example, b and c. This is very interesting. You can change these two numbers without affecting the result. So it means that this becomes equal to b to the log of a in base c. So it is very tricky. Not very tricky. I mean that I am just remembering what I did when I was at your age. That was the hardest one for me to prove. Okay, so none of these numbers are in general equal, but what I'm claiming is that if you have this condition, if you want to, you can interchange these two without the result being changed at all. If you are interested, I recommend you to think about these problems as well. Okay. Now, if I end, unfortunately, right here, it's not very good because you might forget things, but let me see. Is there something nice here? Okay. Let me give you something to simplify. I want to see how many of you can simplify this. Okay. So try to send these formulas to your memory. It's not hard. So we know that x is positive. We know that y is positive. We know that x is not equal to 1. We know that y is not equal to 1. Assume that I have given you all these conditions. But I want you to simplify this expression as much as possible. And probably in the most efficient, of course, this is a little bit subjective, but yeah, try to do it efficiently. I pause recording and I wait a little bit for you, okay? Okay, Ali, your answer is correct. So how did you got the answer?
So first I got rid of the 1 over on both sides by interchanging the base and the...
Yeah, so we just learned 1 over a log can be written as a log. How?
By
interchanging the role of these two. So the square root of xy goes here, x goes there. Yes or no? Plus, what can I do for the next one? The same trick. And then it becomes super, super simple, yes? Now, which formula you use? Can you tell me?
The multiplication.
Yeah, because we have two logs with addition between them. And then, fortunately, the bases are the same now. So I can collect it to what? A log with the same base, but the price that I have to pay to collect them is to change this to multiplication. As simple as that. And the question is asking you, what is the number so that when this raised to that power becomes xy? What's the answer? It's just simply 2. If you don't like this, you have an alternative. You can say that the log xy, instead of the square root of xy, I can write xy to the power of 1/2. But this 1/2 can go back, but I need to swap. It becomes 2 log of xy in base xy. But any log of any number in its own base is 1, and then 2. The answer is 2. So it was very, very simple. But if you don't know these rules, it becomes complicated. So I really want you to learn these 2 formulas as well. So I don't know, I haven't checked the book, but I know in Origo book these are not there. So, but you need to learn how to use them. So there are some nice problems. Let me just at least give you some of the chances. Okay, I want to write one. This is not very hard, but I think you will like it. Okay, so let me see which one is better probably. Okay, let me, are you ready for a little bit of challenge or not? Okay, so let me write something numeric, okay? So I want you to simplify this expression as much as possible. Log of 2 times the square root of 5, but in the base of 5th root of 5. Yes? Minus logarithm of 5 times the square root of 5. The base is 3rd root of 5. Then I would write logarithm 4 plus 4 square root of 3. 2 square root of 3, sorry. 2 square root of 3. But the base is a square root of 3 plus 1. Yeah, that's it. I want you to simplify, well, of course, without calculators, as much as possible. I mean, if you can really solve this, you don't have any problems with logarithms at all. But it doesn't mean that we can solve all the problems. The problem is very hard. Even I myself cannot solve it. I have to think a lot. So this, let us see how many of you can solve this one. So but let me just check everything I have written correct. 2 square root of 5, 5th root, yes. Yes, yeah. I don't think, in principle, you shouldn't have problems, these two. This might be a little bit tricky. And if you discover the pattern, it's not tricky at all. That one is simplest of these 3. The simplest. Because the time is finishing, let me just do it for you. And then we will do some of these problems later. More or less the lesson of logarithms is finished. There is one more important part of this lesson is left, and that is solving logarithmic equations, which is probably the most important part. But you need to know the rules for logarithms in a nice way so that you can use them when you want to find solve logarithmic equations. So let us do it together. And I want to hear from you, okay? So what is your opinion? If you don't mind, let us start with this middle one, because I don't think that's a problem there. So what is your opinion about this? Can you help me to simplify this as much as possible? So logarithm of 5 square root of 5, 3rd root of 5. So how do you proceed if you want to start? According to the rules that you learned just today, yes? What can you do with this one? What can I write? 5?
Power of 1.
Yes, exactly. That's good. But what can I write for this one? It's 5 times 5 to the power of 1/2. Yes? Yes or no? But then 5 to the power of 1, I can write it a little bit more. So this let me just for the time being, don't be in hurry and keep it here. But then, do you agree if I write 3/2 here? Yes? Because the power that is not written here is 1, and this is 1/2, and I add them, it becomes 3/2. But now, what can I do? I can move this directly to the back. So this becomes 3/2. But this one, I have to calculate the reciprocal and move it to the back. The reciprocal is 3/1. And what is left? I have a log left. The number in front is 5. The number at the base is also 5. We are done. So this becomes 9/2. Log of 5 in base 5 is 1. That's the answer. Yes or no? Yeah, please check. If there is some part you don't understand, please let me know immediately. That's on to you. If you don't understand and don't ask question, that's up to you. Yes, please, Tim. Is that understandable? Okay. Now, this one is a little bit problematic here because I really don't know how to get rid of that too. But what can we do? We have to live with it, yes? So what we do is log 2 square roots of 5, 5th root of 5. I can do the same trick, but I cannot simplify it more than that. So I can write log 2 times 5 to the power of 1/2. Here I can write 5 to the power of 1/5. This one I can put it back by making it the reciprocal, so it becomes 5. And then I will have log 2 times 5 to the power of 1/2. And then I have 5 here. But then I have another rule. So if you don't mind, let me put a pair of brackets around it. But then this is a product. So I have 5 here. I open a pair of brackets. It becomes the log of the first one plus the log of the second one. But then what happens? This I cannot simplify more. But this one I can simplify. So I put this 1/2 here. So this becomes 5. This becomes log 2 to the base 5. And then this goes back. You can calculate it in your head. This goes here. 1/2 log of 5 in base 5 is 1. So this becomes just 1/2. And if you want, you can multiply. So it becomes 5 log of 2 base 5 plus 5/2. This cannot be simplified more than that, apparently. So we have to stop there. That's why I'm saying this is not a good number here. Okay? But what is your opinion about the last one?
Squaring rule.
Pardon?
It's squaring rule.
A squaring rule. So what is the answer?
2.
It's 2. So I don't know how you should detect these things, but if you train your eyes, you will catch the patterns immediately. Why is that? Because if I ask you to raise it to power 2, what do you get? The first one is squared, 2 times the first one times the second one. The second one is squared. But then suddenly this one and that one becomes 4. Yes? So this means that, so you need to train your eyes. That's the whole thing, that you need to see the patterns and regularities, yes? So here this becomes logarithm of square root of 3 plus 1 to the power of 2, and then you have the square root of 3 plus 1. Now if I ask you, what is the answer to this? 2, yes, because this 2 goes to the back, and log of any number in its own base is 1. So this becomes 2. Or you can say, to which number I have to raise it to become this. That is 2, yes? So the last number is 2. The middle number is minus 9/2. And unfortunately, the first one cannot be simplified more than that. Okay, but let me just combine everything now. So the question mark finally, and by the way, that's a good I would consider it a success, yes, because I have simplified it quite well. So this question mark becomes equal to, the first number is 5 logarithm of 2 to the base 5, and then plus 5 over 2. That is the answer to the first part, minus the answer to the second part is 9 over 2, plus the answer is 2. And then 5 over 2 minus 9 over 2 is minus 4 over 2. Minus 4 over 2 is minus 2. And minus 2 and positive 2 are gone. Yes? Everything is gone. So what is left is 5. So it was not that bad, by the way. Yes? Yeah. It was not that bad because this expression seems a little bit horrible, but that expression is under control, yes? So I would say that at least I didn't succeed to get the final answer without calculator, but I was able, so assume that you want to punch this your calculator. It's harder to punch that expression your calculator. Yes? Is that clear? So if you really understand, this is not an easy problem, that's a hard problem. But if you understand step by step what is going on, you really don't have any problems with logarithms, unless you forget about the rules. I will spend one more session tomorrow to give you some more interesting problems. Tomorrow we have 2 hours. So 1 hour I will give you examples, and then 1 hour we will practice on them. Okay? And then on Thursday we will teach the next part, that is logarithmic equations. Thank you very much.
Klockan i idrottshallen och den där klockan exakt en timme sen.